Click the button. All right. So, as always, logistics. I sent you all an announcement yesterday where I sent you a couple links to some Google Sheets that basically let you calculate your grade depending upon exam 2 and your final grades. So I just want to walk through how this thing works just to make sure everyone understands how it works, and use it or don't. My feelings aren't hurt either way. So in web courses, as far as I'm aware, you can tweak various scores and assignments to see how it affects your grade. That's something that exists. The problem is, in Canvas, there's no way for me to show you all 2 of my grading policies, specifically that your final can replace your lowest test grade if it improves your score. And at the end of the course, I'll calculate your grade with and without Top Hat, and I'll take the higher of the 2. Those are 2 grading practices I do that Canvas doesn't have any way to automate. So it's something I have to do at the end of the semester myself. I download the whole grade book, do some Excel things. It's not a big deal. But you all can't kind of play around in Canvas to see that. So I made this Excel document, and I'm going to show you all how it works. This is the example file. So this is the one that you all get. It's going to look like this. It's going to have a bunch of red boxes. These red boxes are where you need to put numbers. If you don't put numbers, it assumes 0, basically. You can see that down here at the bottom. So up top is where you do all the edits. And then on the bottom is kind of the final scores in all the various categories. So here we can see our different weighting. Each assignment group has a weighting associated with it. It's in the syllabus. So your discussion sections are 12% of your grade. Your Top Hat is worth 13% of your grade. The quizzes are 25%, test 1 is 15%, test 2 is 15%, and the final is 20%. So great. All that's in the syllabus. So what you do is you go on web courses, you find your current grades in each of these sections. Say in discussions, you've done pretty much everything, 95%. Say in Top Hat, 98%. Say in the quizzes, you have a 92%. I'm putting really high percentages because these should hopefully be really high for everyone because they're just if you did it, you got the points kind of thing. And then the test 1, maybe that's lower. We'll just put the average from the last exam, which was, I think, a 59. I'm not sure after free response how much that went up. Whatever, 59, 60, whatever. And then notice that test 2 total is red. This calculates the average of the 2, whatever. So your current grade in the class is, down here. If you want to get a better sense of what your current grade is, you need to put test 2 total in. So you need to make a guess, and you can play around with the numbers. Say, man, I really want to get a 70 instead. So great, you put a 70, and it spits out your current grade in the class with Top Hat and without Top Hat. You can kind of look at those 2 and whatever. Really, though, what you're going to want to do when you're using this thing is you're going to want to play with test 2 total and the final. You're going to want to play with both of these. If you are just using this, remember I told you all, if you earn 60% or above, you get 60% or above average, you get a B. And that kind of reflects here. Currently, though, what's happening is the tests aren't carrying the full weight. Currently, this the effort base of the course is carrying a lot more significance because we haven't factored in the final yet. The final is worth 20% of your grade. We've only calculated 80% of the points so far. Anyway. So make up a grade in the final. Say on the final, let's just see what happens if I get a 65. It will then spit out the final grade that you earn in the class. With Top Hat, without Top Hat, it's going to take the higher of the 2. You can see that here. In this case, with Top Hat was a 80.39. Without Top Hat was a 77. It picked a bigger number. And then something I'm going to also point out now. Before I point this out, again, don't edit this bottom part because it's a bunch of equations and things like that. But what I want to show you all is the discussion. Great. 95, 95, 98, 98. Quiz, it just takes these numbers. But what I want to point out is notice that your test 1, it shows you, test 1 got replaced by 65. because that was the final exam score. 65 is bigger than a 59. It replaces that one. Yay. So you can see which test would get replaced, and you can see that these would be the final scores in each of the categories and all the things. Lets you see all the stuff. Great. So that's there. Use it. Play around with the numbers. I have no idea what you're going to get on test 2 and all that. You got to play around with it. Yeah.
Does this include the points from the extra credit?
This does not. That's a great question I forgot to mention. If you all did the survey at the beginning of the course, and if you do the post survey, I say survey, not the survey, the pre and post assessment. That's in a separate web courses. If you do both of those, I believe it adds 1% extra to your final grade. I believe that's the case. So take whatever it says your overall grade here and just add 1 to it. That's how that'll work. So great, this exists. You can play around with the numbers and basically see what, assuming that you keep doing the discussion section, top hat quizzes, the same you've been doing, assuming you keep those the same, you can see what you need to score in test 2 / what you need to score in the final to achieve your dreams. And there you go. The last thing I want to point out here is something I haven't necessarily mentioned up to this point, but it's something that I'll just say it now. So in your all's syllabus, I have like the grading scheme. And the grading scheme is what you expect. 90 and above is an A, 80 and above is a B, 70 and above is a C, all that jazz. What I want to mention to you all is when I calculate grades, I will round up. So this is actually already built into Canvas. So this means if you have an 89.01, I just round it up to a 90. I just always round up. I don't make any judgment. Like if it's an 89.4, it rounds up. 89.3 rounds up. If you get an 89 flat, which is like that'd be crazy to get that number, it stays an 89 and that's a B. So the rule, and I will not adjust that any further. So I already kind of built in that I round up, so there's a little bit extra kind of there. But I don't do any further than that. So there you go. There's that in mind. 89, if you have any number that's above an 89, it's an A. Any number above a 79, it's a B. Any number above a 69 is a C, and so on. The other thing I can tell you all, the final is basically, very likely, it's going to be like 40 questions, multiple choice. There's no free response on the final. The reason is I only have like 4 days to grade everything, which is not enough time to grade free response stuff, so it's just a constraint. Free response is great, but I just don't have the time to grade it. So about 40 questions. You all will have 2 hours and 50 minutes, just like every final you've ever taken. So you should have plenty of time for the number of questions. It's a bit of I don't want to use the word marathon, but in some ways it is. In some ways it's a lot of cognitive load for a long period of time. I get that. Though in this case, I can make the argument, the value of it. If you all have to do the MCAT or any other graduate exam, the MCAT I think is 7 hours of just a gruel. And then if you are going into the medical field, yeah, your brain's going to be used for a long period of time in an intensive way. So there is some value to learning to use your brain for long periods of time, even though it's a marathon, but learning to run marathons is, in this case, valuable. Whatever. But it shouldn't be too bad. Yeah.
You have to stay with it.
No. Yeah, it's like every test we've done, where when you're done, you can leave. Most people finish before the 2 hours and 50 minutes. Like 2 hours and 50 minutes, my experience has been it's great that I can finally give you all the time I think you'll need. I'll basically design the test actually around 2 hours, 2 hours, 10 minutes. And the 40 minutes is kind of the extra. So when I kind of time it out, you get the full 2 hours and 50 minutes. But the hope is that you have way more than enough time so you can check your work and all that jazz. For the final, that's something nice by having that big block. Okay. Any other questions about any logistics stuff like this? So yeah.
So the final replaces a grade if it's higher, but it's not like there's a drop. Like if you're okay with
No.
yours and one exists, you still have to take the final. Right?
Yes. Yeah, you still, because the final is cumulative, which I know is very unpleasant. Cumulative finals suck. I remember that. But teaching-wise, my logic is by the end of my course, I want to assess if you know. By the end of my course, your grade should reflect if you know all the things in the course. And so the final being cumulative is a measure at the end of the course. Do you know all the things in the course? And that's also why I can replace a test grade, because say you did bad on test 1, but then you learn the stuff and on the final you do great. Then it replaces the things that you didn't know. Like, then at the end of the course, you know your stuff and you don't get penalized. Like, then you've checked the box that I want you to check. So that's also the logic. The reason I have your all's final replace the lowest test score isn't because out of like the kindness of my heart, like, yes, I do it kind, but it's actually from like a pedagogical standpoint of like, if on the final you do great, then your grade should reflect that. And that means you learn from your mistakes. Awesome. That's the goal, right? That's the reason. And the reason it doesn't replace both tests, though, when you make something worth too many points, people are more likely, it increases pressure and also increases the likelihood people are going to do nefarious things. So like, that's why I have to strike a balance with, I don't want one test to be potentially worth 50% of your grade, because then that incentivizes people to maybe compromise morals. If you make something worth too much, people tend to get a little bit sketchier on things. That's just anywho. That's my thought process there. Okay. The last thing I'll mention about the final will be about 70% or so of stuff from test 1 and test 2. And then the other 30% will be the stuff we cover after test 2. So it's mostly the stuff from test 1 and test 2. The other 30% will be the rotation stuff we learn after test 2 finishes. All right. Any other questions? All right, great. Again, play around with this. It should all work. And yeah, you can see what happens. So like, 59 and 70, say you score a 55 on the final. Notice that neither of the test 1 or test 2 changed to a 55 because it was below. So it doesn't penalize you. If you do worse in the final than test 1 or test 2, it does not replace one of those grades. Great. Okay. There's that. It exists. Use it or don't. Oh, yeah. Someone reminded me. I keep forgetting to tell you all jokes. All right. I was very lonely, so I bought some shares. It's nice to have a bit of company. So anywho, if you all remind me, these are curated by my wife. She went through many Reddit threads and websites to find clever word jokes, but I've forgotten to tell them the entire semester, so you missed out. But if you remind me, I'll keep telling you. All right, last class we talked about momentum. Momentum is a really, really simple thing to calculate. It's just m times v, and it's really, really useful. So there it is, m times v. It's a super, super useful thing in physics because it's a conserved quantity. Conserved meaning what you start with equals what you end with. And physicists love conserved quantities because then you can figure out stuff and all that jazz. Physicists honestly stop working with velocity and just start doing everything in terms of momentum at some point, which is kind of interesting. You don't need to worry about, so like kinetic energy, if you all remember, kinetic energy is 1/2 mv squared. When physicists are actually writing equations for kinetic energy, they don't use 1/2 mv squared. They use 1/2 p squared over m. They're the exact same thing. You can see that if you just so they actually write it, it's the same thing, but just p squared over 2m. P squared over 2m is the exact same thing as 1/2 mv squared. But it's just one of those fun things. Physicists love momentum. You don't need to know that. But it's interesting. So, momentum, m times v. Super, super useful thing it's conserved, yay. What does conserved mean? It means that, if I keep scrolling, there's a slide, there it is. Momentum I start with equals momentum I end with. If you add up all your momentums that you start with, they will equal all the momentums you end with, as long as there's no external forces acting on it. As long as there's no gravity speeding things up or friction or applied force. I'm never going to give you a problem where there is extra forces acting on it. So you don't need to worry about that. So yeah, long story short, if you have two things colliding, you can assume in this class, you can assume this to be true. It is a vector, so notice I wrote it two different ways. You got to add up all your x momentums in the beginning equals all your x momentums at the end. You add up all your y momentums in the beginning. You add up all your y momentums at the end. And yeah, that's all we're going to do for the rest of the class is just practice that. Building this equation. So I gave you all three. Oh, and then in elastic collisions, energy is also conserved. We'll see that later. So we worked through one of these. I said, hey, you got two objects. They stick together. What's their total mass? You have two objects, each moving. What's their momentums? M1, V1, M2, V2. Add them together. Great. Two objects get stuck together. What's their mass? M1 plus M2. And then we put it all together. And we built our first conservation momentum problem. I got two objects, each with their own momentum. And then at the end, they get stuck together with its momentum. And you set them equal and yay. I then showed you all this slide, and I said, do not use this slide to figure out how to solve problems. The purpose of this slide is not to give you formulas that you're going to reference. The purpose of the slide is to give you examples to show you what it looks like. So, just to remind you all, the first one is if I have two objects, so pretend like this doesn't exist. The first example was this picture on the right here. Two objects are heading towards each other. They bounce off each other. Right conservation momentum. Well, I got momentum of object 1 in the beginning plus momentum of object 2 in the beginning equals momentum of object 1 at the end plus momentum of object 2 at the end. Great. The next one is I had two objects heading towards each other and then they collide. Object 1 momentum plus object 2 momentum in the beginning equals... They're just examples. They're just examples to show you what it looks like. We're going to practice them today, but please do not jump to this slide and use it to build it. Every single problem when you're solving this, momentum's initial equals momentum's final. This is the equation. Build it yourself. Build it yourself, because if you don't learn how to build it yourself, what if I give you a problem with three objects? None of these work. And you can basically guarantee if I give you a free response, it's not going to fit into one of these categories. So I don't want you to get in the bad habit of relying on these. I want you to get in the habit of learning how to learn how to do this, learn how to build this, learn the skill. That's what I need you all to know. So if there's a collision or a separation, so if you have two objects colliding or objects starting together and they split up, you're going to use conservation momentum, draw a picture of the beginning and the end, and where the objects are, identify a type of collision, go through the process, X and Y, all that good stuff. Okay, and now we do. Two figure skatings. Yeah, the rest of the class is literally just doing this. Maybe we'll get to center mass today. If not, we'll do center mass on Thursday and start fluids then. Two figure skaters are coasting in the same direction, with the leading skater moving at 5.5 meters per second, the trailing skater moving at 6.2 meters per second. When the trailing skater catches up with the leading skater, he picks her up without applying any horizontal forces. Again, no extra stuff's getting added to it, no extra forces. The trailing skater is 50% heavier than the 50 kilogram leading skater. What's their speed after he picks her up? Draw a picture. Beginning and end. That's the key. Again, check around, chat with the people around you, see if they drew the same picture, or at least it looks similar. Anytime I have you all working on this, please work with the people around you. Yeah.
I'm assuming the word 50% heavier means it's 1.5, not.
Yes. Yeah. 50% more. Yep. All right. So in the initial, you got blob 1. That's the trailing skater, and they're moving. Velocity 1 initial equals 6.2. And then you got blob 2 moving along. If you call this V1 and V2, that's fine. I put the V1 initial and V2 initial. It just helps with being more precise and having a better sense of, oh, this is the beginning. By putting little eyes next to it, you know it's the beginning. Because otherwise you don't know whether it's the beginning or the end if you look at these. So great, there they go. And then the blobs are connected. They pick them up. If you want, you can put blob 2 on blob A. It really doesn't matter. They're stuck together. However you want to make that happen. They're stuck together and they're moving to the right. Awesome. Instead of doing our givens, let's actually, remember I told you all one of the skills is like, what are you even solving for is actually one of the first things you should decide. What are we solving for? Yeah, velocity. I kind of wrote it already as a question mark, but hopefully you recognize that in the problem that says, what is their speed? Their speed together. They're stuck together. So yeah, step 2, VF equals question mark. I didn't put VF1. I didn't put VF2. They're stuck together. So I don't need to specify object 1 or object 2 because it's shared. And my initial stuff is all kind of here. I'm actually going to put it in the picture. So mass of 1, when we're talking about momentum, there's only 2 things you need to know. Mass and velocity. That's the only thing we care about. So we should ask ourselves, hey, great, we got their velocities, what's their mass? The trailing skater is 50% heavier than the 50 kilogram leading skater. So the leading skater is 50 kilograms, easy peasy. I do want to remind you all that this is mass, not weight. And the reason I mentioned that, it doesn't actually change much. Doesn't really change anything, but that's just a reminder to you all. Kilograms is mass. Now the reality is they're both on the same planet. So they're both being affected by gravity. So if you're 50% heavier on Earth, you do have 50% more mass. Like, that's going to be true. If you're 50% heavier, your mass is also going to be 50% more because your Fg equals mg. Everything's on Earth. G is always the same. So whatever. Great. What's the mass of the first person? 75. It's 1.5 times 50. Or take half of 50 and add it to 50. However you want to phrase that. Fantastic. How are we going to solve this problem? There is a collision. So we are going to sum up all our momentums in the x, and that's going to equal the sum of all our momentums in the y. Or sorry, not the y. All our momentums in beginning x equals all our momentums final x. All our momentums beginning y equals all the momentums final y. I'm writing both just to get us in the habit that there's x and y, and you got to keep them separated. Now, the reality is one of these we don't care about. Which of these do we not care about? Yeah, we don't care about the y because there is no up, down at all. 0 equals 0, yay. But I mention it just because literally the next problem we're going to do is going to have x and y. So I want to keep that somewhere in your brain. I want us to not forget that that's a thing. So then I just copy and paste this. Once you draw a pretty picture and once you have all your givens and all this jazz, you don't need to read the problem anymore. So boom, this goes here, and then build it. Try it yourself. Build the momentum equation. What is the momentum's initials? Add them together. What is my momentum's final? Write it out in terms of variables before you plug in numbers. Do it all in terms of variables before you plug in numbers. Once you plug in numbers, it's really hard to keep track of what's what. And again, chat with the people around you. Check what they put. See if they put the same answer stuff you did. If not, one of you is wrong or both of you is wrong. All right, so how many objects do I start with? In my initial, how many objects are there? 2, so they each get their own momentum. You have the momentum of object 1 in the beginning plus the momentum of object 2 in the beginning. If you had 5 objects, you would add up 5 of them. Equals, how many objects do we have at the end? 1. I'm going to call it like P1, 2, because they're together. Call it whatever you want. Great, and then we just write momentum is m times v. So just chuck a bunch of m times v's in there. So this means, and I'm going to do it over here for the sake of space, because I am totally going to run out of room otherwise, m1 v1 initial plus m2 v2 initial equals. I have one big object at the end, everything's together, m times v plus m times v equals m times v. You just got to make sure to keep them together. Mass of 1, velocity of 1. Mass of 2, velocity of 2. And then you just plug in numbers, and then that's it. And this is the only way to solve this problem. So like in previous problems, we've had like, you could do this, or this, or this. When we have collisions, momentum is the only way to solve this. There's a lot of complex. So like what's interesting here, you don't care how quickly they picked up the person. You don't care if it was like a weird like swooping motion or something like that. What's really cool is you don't care about how he picked him up, you just care that he picked him up, and this works. Like assuming no other forces are acting on it, friction, stuff like that. This gets you what their velocities are going to be, which is kind of cool. Another example, this is like throwing silly putty at a door and it sticks to it and then whatever. There's all sorts of like random problems you could do with this, but all right, and you just got to make sure, the only thing you have to make sure at this point is that you put the right numbers in the right spot. That sounds obvious, but it's really easy to mix up the velocities. It's really easy to accidentally put the wrong number there. So just be careful. Take your time. My second person has 50 and they're moving 5.5. And this is where the picture is helpful. They're all nicely together and all that good stuff. So yeah, we have 75 times 6.2 plus 50 times 5.5 equals 75 plus 50. And if you do all the math, I'll get a calculator. You get their final velocity, and it's great. Nice, straightforward, lets you do nifty things. So at the end of the day, you get the left side is 740. And this will be 125. And you get 5.92 meters per second. It's somewhere in between the two. You're not as fast as the first person. You're not as slow as the second person. They kind of combined in some way. And great. So there you go. That's kind of the easiest example of conservation momentum. And now we're going to build on it. Each example I give you after this is going to add another layer of complexity. That's the idea with these. Because momentum is so straightforward, we can do that. Where we can like start with a simple one, then build and build and build and build. Before we do that though, I want to see if you all are capable. Did you build the equation? Or did you get it from the previous slide? I'm not going to make this top that question because it'd be a nightmare to type in. But I want you all to try this. I'm going to give you a few minutes to do this. Objects 1, 2, and 3 are all moving horizontally. They're separate from each other. They're all separate from each other. They all collide. And object 1 and 2 get stuck together while object 3 bounces off. Make the equation. Make up their initial velocities. Object 1 has velocity 1 initial. Object 2 has velocity 2 initial. Object whatever. Can you all build the conservation momentum equation for this? All in terms of variables. If you draw a picture, try writing it out. This is the skill. And I just clarified they all start separate from each other. All right, so you got 3 objects. I don't really care which way these objects are moving. Doesn't matter. I just need them to run into each other. That's all that matters. At some point, they have to run into each other. However you want that to happen, great. It doesn't even matter which objects run into each other first. Doesn't matter. We don't care. We just care about the beginning and the end. That's the cool thing again with momentum. Don't care about the order of interactions. Just care about they hit each other. To me, it's kind of crazy all this stuff kind of works. Great. They all start separate and they all eventually will hit each other. Awesome. They collide. Object 1 and 2 get stuck together. Don't care which way they move. Doesn't matter. We don't put positives and negatives when we're building this equation. We let the mat, we'll put those, if the velocity is negative, then we'll put it as negative. But we don't write it in the equation. Great. So they're stuck together and object 3 is, let's just say it's going off to the right. Who cares? Doesn't matter which way they're going. And then you sum it up. There's only x direction, so we're just going to do momentums in the x initial equals momentums in the x final. And you just ask yourself, how many objects do I start with? 3. So each one gets their own momentum. Momentum of object 1 initial plus momentum of object 2 initial plus momentum of object 3 initial equals. How many objects do I end with? 2. I've got momentum of object 1, 2 final plus momentum of object 3 final. Great. 3 objects in the beginning, 2 objects at the end, and then you just chuck a bunch of m's and v's. So m1 v1 initial plus m2 v2 initial plus m3 v3 initial equals m1 plus m2 v12 final plus m3 v3 final. M times v, m times v, m times v, all the m times v's. You just keep them together. Initials on one side, finals on the other. There you go. So that's the skill. You can make up so many of these, pretty straightforward to make up these problems. All right. So, great. One dimension, as I told you all, I could totally give you 3 objects. And this would be as kind of funky as it seems, I could totally give you all a problem like this on a multiple choice question where each answer is the equations. That'd be fine. This could be a problem I could give on the exam of, hey, what's the right equation for the following interaction? Kind of thing. Okay, so we are not going to do the boy and the boulder. That is actually the last problem we're going to do because it is, as weird as it sounds, it's the most complicated due to math reasons, not due to physics reasons. So we're going to leave the boy and the boulder at the end. So we're going to build. A falcon, a 0.9 kilogram falcon, is diving at 28 meters per second at a downward angle of 35 degrees. It catches a 0.325 kilogram pigeon from behind in the air. What is their combined velocity after impact if the pigeon's initial velocity was 7 meters per second directly horizontally? So actually, again, we're going to start. Normally I'd say draw a picture, but let's actually get in the habit of what are we even solving for? It's always good to have the target in mind before you even do anything else. What are we even solving for in this problem? We're solving for their combined velocity, which is at the end, which is final velocity. Good. It's good to have the goal in mind. If you don't know the goal, you'll never hit your target unless by pure chance, and that's not a good thing to bank on. All right, we already have a picture. We have a picture of the beginning. If you want, you can draw a picture of the end. So there's my beginning. And then my end, there's bird 1, there's bird 2. They're stuck together and they're moving. Great. You have to know that they get stuck together. If you don't know they get stuck together, you're never going to solve this problem. All right. And yeah, we're going to call bird 1, bird 2. It's way easier than saying falcon and pigeon a bunch of times. Okay, awesome. Now the next thing that hopefully this raised a flag in your brain, anytime you all see an arrow with an angle, what do you immediately know you're going to need to do at some point? Break it into X and Y. Go ahead and do it. You're going to have to do, like, anytime you all see that, that should be a trigger. You're going to have to do it sooner than later. Even if you don't know why you're doing it, just do it. But label your triangle with what the two sides represent. That is a good practice. So there's our triangle, V1 initial. Make sure you label the other two sides of your triangle and make sure you draw them as arrows so you don't make a silly mistake. I'm going to make the arrow a little bit bigger just so I don't make my line over the 35. It's the only reason I'm doing that. Otherwise, this is kind of hard to read. So, great. I make it into a right triangle. If you didn't draw those sides as arrows, you should do so. So, you, again, that you don't make a mistake. Which way should the arrow on the bottom point? Right or left? To the right. So is this is my V1 initial. Is it the X or the Y? This is my X component. Because it's to the right, is that going to be positive or negative? That one's going to be positive. And this is going to equal 28 times cosine of 35. Why is it cosine? Because it's the adjacent side. Adjacent side gets cosine. Opposite side, that's going to be V1 initial Y. Velocity of object 1 in the beginning, in the Y direction. Is that arrow up or down? The falcon's going down. How do I know it's going down? Because if you look at that, that arrow's going to, like, which way is the falcon going? Up or down? Down. That's the way to figure that out. Is this positive or negative? If you all forget the negative here, you will get the wrong answer. This is one of those, the direction matters. Whether you're going up or down matters. And if you forget to put the negative, you will get the wrong answer, because if you put it as a positive, you're saying this falcon is going up and to the right, not down and to the right. And up and to the right and down and to the right are very different. Whether or not a plane goes up or down matters a lot. So, anyway, negative 28 times sine of 35. Why is it sine? Because it's the opposite side. And each of these equals something. So the one down here is 22.94. That's my X component. And my Y component is going to be negative 16.06. I can almost guarantee, if I didn't say anything, that at least 30% of people would forget the negative side. Just based on my experience doing these problems. So, and that's 30% of people that would get the wrong answer. You got to be careful. Like, this is one of those ups and downs matters. This is where a picture comes in handy. And this is why when you draw a triangle, you draw arrows on that triangle. That helps to make sure you don't make that mistake. All right, so great. My givens are all kind of here. I'll check my mass here. The mass of the falcon is 0.9 kilograms. The mass of the pigeon is 0.35. So I'm not going to bother writing all the givens again because they're there in my picture.
The mass of the pigeon is 0.325.
Oh, thank you. That would mess things up. Yes. Mass of the pigeon is 0.325 kilograms. Thank you. We'll do that there. All right. How are we going to do this? Sum of momentum's initial in the x equals sum of momentum's final in the x. Sum of momentum's initial in the y equals sum of momentum's final in the y. You have to do it twice. And you go through the same logic. How many objects do I start with? How many objects do I end with? The only thing you got to be careful of is x needs to be all x components, y needs to be all y components. Do not mix your x and y. X and y, oil and water. Do not mix. Keep them separated. At the very, very end of the problem, we'll be able to combine x and y with Pythagorean's theorem. That's at the very last step. So how many objects do I start with? 2. How many objects do I end with? 1. That is true of both of these cases. So space gets a little premium here. I'll write this one out. So mass 1 times V1 initial here. I'll write it in 2 steps. P1 initial x plus P2 initial x. 2 objects. Each have their own x component. Equals P12 final x. Because they're stuck together. Okay. Then we do the same. Well, then we M1 V1 initial x plus M2 V2 initial x equals. Definitely don't have enough room here. Equals M1 plus M2 V final. M1 plus M2 times V final X, and that's hideous, so I'm going to go ahead and shove everything to the other page. It's not ideal, but whatever. Yay! And, we're just going to plug in numbers for that V final X. Great! We built our X1. Now we're going to build our Y1. M1 V1 initial Y plus M2 V2 initial Y equals M1 plus M2 V final Y. The X and the Y equations look literally the same. You just swap out X's and Y's. That's it. And plug in numbers. Like the last part, the physics is done. So now we just plug in things. So step 4, 0.9 times the initial X component, which is going to be 22.94, plus 0.325 times 7 equals 0.9 plus 0.325 times the velocity final. And that's what we're solving for, V final X. If you just plug that in a calculator, do the algebra, you'll find that V final X is 18.7 meters per second. Add up everything on the left. I'll go ahead and do the steps, but the algebra should hopefully be the easiest part of any physics problem I give you. That's the dream. The hard part should be the physics. All right, so great. 22.921 equals 1.225. You divide, and now I can feel okay with just putting the answer. 18.711 meters per second. Great, that's my velocity in the x. Then you do it for the y. In the y direction, now what's nice in the y direction, I'll write the whole thing. 0.9 times negative 16.06. Again, if you don't put the negative, you will get a completely wrong answer. Times 0.325. What's the pigeon's velocity? In the beginning, is the pigeon moving up or down at all? Nope, it's got zero velocity in the y direction. We wrote out the whole thing just to see how to do that, but it doesn't have any in that direction. And then the right side's the same. So it's just like the problem we just did. The only difference is you got to do it twice. Just like 2D kinematics is just like 1D kinematics, you just got to do it twice. And you got to realize where accelerations go to and all adjustment. So the left side is negative 14.454. 0.454 equals that 1.225. Divide things. And you get negative 11.8. And there's our answers. You know, you can see them there on the bottom. The last thing I'll mention to you all. So in this problem, the answers are in vector notation, just to make it a little bit easy, one less step. But I do want to make sure you all remember this. So I'm not going to actually work out this next part, but I think it's good practice for you all. If I wanted the magnitude of the V final, I'm just going to straight up tell you the answer. And then that's a good exercise for you all to try on your own. How do you, now that I have the x and y components, how do I get the magnitude? So I'm going to give you all the magnitude is going to be 22.11. And I'm also going to give you the angle of that, and that's going to be negative 32.24. And this is just good vector practice. So do you remember how to work with vectors is basically that last little part tacked on the end. But I'm not going to spend the time on it because it's not a new skill. Yay, that's the next level of complexity. We've done momentum in one dimension. Now we've done momentum in two dimensions with momentum in one dimension with two objects, momentum in two dimensions with two objects. What's the next layer of complexity? Momentum in two dimensions with four objects. It's not as bad as it seems. It sounds bad. It's not going to be that bad. Momentum is a very straightforward process. When we get to the boy in the sled, the math there is going to be unpleasant, and we're not going to even do the math. I'm going to show how to set it up, and then we're not going to do the math. And then we're not going to have a problem like that in the test, but I just want to mention it. There's a tiny bit there's some value in it in the concepts. But yeah, this one's really, like, I could totally ask this problem as a free response problem on the exam. This one is not, you're like, oh my gosh, so many objects. You'll see, it's really not that bad. So, 3 70-kilogram deer are standing on a flat 200-kilogram rock on an ice pond. A gunshot goes off and the deer scatter. Deer A goes up and to the right, deer B goes up and to the left, and deer C goes down and to the right. Find the velocity. What is the velocity of the rock and what's your standing after this happens? Draw a picture. And if you all noticed, I didn't actually read the numbers for the which way they went. See if you all can figure out how to draw these arrows. Again, good vector practice. Can you look at these and tell what direction it is based on these numbers? And you can do that by drawing them. Draw a beginning and draw an end. You need both. If you're missing a beginning or an end, you can't solve the problem. And I'll help you all with the beginning because it's really quick. All right, here's my rock. In the beginning, what are the deer doing? Are they moving or still? Yeah, they're standing on a rock. So what we're going to do in this problem is I'm going to color code these deer. Deer A is going to be green dot. Deer B is going to be orange dot. And deer C is going to be purple dot. Does it matter where I place these deer? Nope, doesn't matter. Another cool thing about momentum, doesn't matter where they are on the rock. All that matters is when they leave this rock, this is how fast they're going. That's literally all you care about when it comes to momentum. You don't care which one leaves the rock first. You don't care if they all leave at the same time. You don't care if one leaves and then 10 minutes later another one leaves. All you care is that when they leave, they have these velocities. And you can find the velocity of the rock afterwards. All right, so on the final, we have the rock. The rock will move. Like, there is technically a chance that the rock doesn't move, but I'm going to tell you that would be a boring answer, that the rock doesn't move. The rock's going to move. Which way does the rock move? I don't know. Take a guess. Let's pretend it's going up to the right. I know that's not actually the right answer, but I'm purposely picking that just to show you it doesn't matter. You're going to find out which way it moves. You don't need to predict it correctly. Let's just, whatever. It's going to move. We picked a direction. Awesome. Is it the right direction? No, doesn't matter. All right, deer C hops off the rock and is going, so great, he's no longer on the rock, and he's going down a little bit to the right, but mostly down. Negative 18 down, positive 1.2 to the right. Then you got deer B. That one is going to hop off. And this is a little funky, but I'm going to go and draw him over here just so I can actually fit it. Deer B hops off to the left because I have a negative X component, and to the right, and up because a positive J component. Great. So that one's to the left and up. And then deer A hops off the rock, and they're going up and to the right, more to the right than up. Great. My arrows are definitely not to scale, but this is just good practice. Do you remember how to draw vectors? It's useful. So great, there they all are. They're off the rock, they're running, who cares? Off they go. What do they do after the rock? Slip and fall, who knows? Doesn't matter. All right, so what are we solving for? We are solving for the velocity final of the rock. That's the problem. What's given? We have the velocity of deer A in the beginning, and that's 15I plus 5J. We have the velocity of deer B in the beginning. That's negative 12I plus 8J. We have velocity of deer C in the beginning. That's 1.2I minus 18J. And we have the mass of all the deers. Mass of deer A equals mass of deer B equals mass of deer C. Mass of A equals mass of B equals mass of C equals 70 kilograms. And we know the mass of the rock is 200 kilograms. We know masses, we know velocities. Yay. We know the initial velocity of the rock. What is it? Great. What's the initial velocity of deer A? Oh, yeah, I did a bad thing. Do y'all see the mistake? What was my mistake? See if y'all can spot it. The initials are all 0. I labeled these wrong. These are all finals. These aren't in my initial picture, they're not moving. I accidentally put I's instead of F's. It's a really easy mistake to do. How did I catch that mistake? Well, I asked, what's my initial velocity? And I realized it was 0, and obviously That means those can't also be 0. Velocity of everything in the beginning is 0. Velocity initial is 0. Everything. Everything's all together. They're all chilling on a rock. Why are they on a rock? I don't know. Doesn't matter. Come up with your own fun story for that. How are we going to solve this problem? The same way we solve every momentum problem. Sum of momentums in the x beginnings equals sum of momentums in the end in the x direction. And then we're going to do it again for the y direction. So again, this problem seems unpleasant, but it's really not that bad. How many objects do we have to begin with? They're all chilling on the rock together. It's one big blob. They're all one big blob. So I've got mass of A plus mass of B plus mass of C plus mass of rock times their initial velocity. They're all together, chilling on the rock. They're all stuck together. It's like someone sitting in a car. And at this point, I'm going to make the executive decision to move to another slide. I know I'm not going to be able to fit this thing in here. Great. Equals. How many objects do I have at the end? 4 objects. 3 deer and 1 brock. So, mass of deer A, velocity of A, final, and the x, plus mass of B times velocity B, final x, plus mass of C, velocity of C, final x, plus mass of rock times velocity of rock, final x. Four things, each with their own mass, each with their own velocity. Great, we did the x component. Oh, you know what's really nice? What happens on the left side of the equation? Yeah, it's just 0. So 0 equals all that stuff. Turns out really nice. I'm going to be through the power of technology, I'm going to make the y component, and I'm going to cheat. I'm just going to copy this entire equation and change these x to y's. It's the exact same thing, just with y's. Everywhere there's an x, magically gets turned into a y. Y, 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 and y. Had so much fun doing it once, you do it again. And I'm just going to go ahead and solve these underneath them, just for the sake of organization purposes. So this side is 0, because the initial velocity is 0. Equals 0. Equals, and you just plug the numbers in. 0 equals 70 times 15 plus 70 times negative 12 plus 70 times 1.2 plus 200 times the final rock, x. And then you solve it. Like, great, find the x component from that. Add up the first 3 terms, divide it by 200. The math here is not crazy. We're not squaring anything. We're not doing any. Just add up the first 3 terms. So you get that v final rock and the x equals, if you add up all the first terms, that's going to be 15 minus 12 plus, don't know why I put a decimal there. 0.2. Great, so you get 200 divided by 200, nope, other way around. You get 294. Oh, and you got to be careful here. You're going to get a negative sign because you're going to move it all to the other side. So you're going to subtract it to the other side and get that divided by 200, and you get negative something. Negative 1.47 meters per second. Yay, there's my x component. The rock's going to go to the left. Oh, my initial prediction was wrong. Oh well, who cares? Then we do the whole thing for the y components. Still equals 0 because my initial velocity in the y is still 0. And we'll pick maybe green just to make it easier to see. That's 0. So 0 equals the 70 times the y components times 5 plus 70 times 8 plus 70 times negative 18 plus 200 times velocity rock final y. You do the same rigmarole, add the things together, subtract them to the other side, divide by 200. So you get negative. The negative is going to come from subtracting it over. Again, you can try this out on your own. I'm going to leave the algebra for y'all. I'll let y'all on your own time kind of work through that. Negative, so this gets a negative 350 over 200. Again, if you're like, where are these negative signs coming from? Just try this on your own, going through it, and you'll see. And you get positive 1.75 meters per second. Great. So long story short, which way should my rock actually go? My rock should go up and to the left. You can fix your picture after if you want. And this is the most complex of a problem I could ask, like many objects, X and Y, yay. Momentum is very straightforward. Very straightforward. The skills that you all been practicing with conservation of energy, initial and final, they're going to transfer to this. What's the beginning? What's the end? Add them all up. The only new thing is that X and Y matter, whereas energy they don't. So. All right, the last problem we're going to do is the boy and his sled. We're going to set up the problem. I'm not actually going to go through all the algebra because it's very unpleasant. But I'm also not going to require you all to go through all the algebra or do a problem like that has this much algebra on the test. This problem will look simple, but we'll see as it develops why the math gets unpleasant. The setup is not bad. Getting steps 1, 2, 3, no problem. Then when you actually solve it, you'll see. So, anyway, a boy sleds down a hill and onto a frictionless ice-covered lake at 10 meters per second. In the middle of the lake is a 1,000-kilogram boulder. When the sled crashes into the boulder, the boy and the sled bounce backwards. It's an elastic collision. That's important. If the boy's mass is 40 kilograms and the sled's mass is 2.5 kilograms, what's the speed of the sled of the boy and the sled boy thing in the boulder after the collision? So, a lot of people get hung up on the sleds down the hill. The only reason that matters is it just explains why he's moving. That's the only reason the hill is mentioned. We don't actually care about the hill at all. Pretend like it doesn't say anything about the hill. So great. Boy goes down the hill. Great. He's now on flat ground. In my initial, my boy is on flat ground because he's no longer down the hill. So we're going to call that velocity 1 initial is 10 meters per second. And you got a big boulder. And the mass of the boy and sled together is going to be 42.5. Boy is 40, or sled is, boy is 40, sled is 2.5. Add them together. Awesome. They hit the boulder. The boulder's not even moving to begin with. And the mass of the boulder is 1,000. All right, so far, the problem's very straightforward. You're like, man, it doesn't even have X and Y components. How could this be bad? At the end, they bounce off each other. Boy goes backwards. Boulder goes this way. How fast is the boy going? No idea. How fast is the boulder going? No idea. All right, so our givens, we already kind of jot them down. Great, there they are. What are we solving for? Same thing, we kind of already identified those. What's the boy doing? What's the boulder doing? We're going to assume the boy and the sled stay stuck together. They're always stuck together, just to clarify that. The boy's not flying off it or anything like that. Okay. Now we build our conservation momentum. How many objects do I start with? 2. So we got our boy who's moving, plus our rock, which isn't, but I'm still just going to write it here. At the end, how many objects do I have? 2. equals the mass of the boy times the boy's velocity times the mass of the boulder times its velocity. Again, at this point, not too bad. Oh, look, the second term even 0 because the boulder's not moving. So that term goes to 0. Okay, awesome. Doesn't look too bad. Let me plug in numbers, and if you haven't spotted the roadblock yet, you're going to spot it very quickly. So the boys and sleds thing is that times 10 equals 42.25. That's the mass of the boy times their velocity, don't know it, times the mass of the boulder times the velocity of the boulder, don't know that. Can we solve this? No. How many missings do we have? How many equations do we have? 1. You cannot solve 2 unknowns with 1 equation. So then the follow-up is immediately, I need another equation. And what equation is that going to be? And this is where I scroll back to the slide that talked about elastic collisions. Elastic collisions are special. And what's special about them is this. Not only is momentum conserved, energy is also conserved. So the energy I start with equals the energy I end with. This is only true of elastic collisions. Inelastic, where things get stuck together, energy is not conserved. Really easy to kind of understand that. When things get stuck together, they deform. Energy is lost in those deformations. Think of like if I chuck some Play-Doh at the wall, or chuck some Play-Doh at like a door or something like that, and the deformation, it was moving, and then it's not. Kind of thing. Like, energy is not conserved when things squish. And they stay squished. In this case, though, they don't squish and stay squished. They bounce off each other. In your all's lab this week, this is what you're doing, is elastic collisions. And you're going to actually see that hopefully energy is conserved and momentum is conserved. It's 2 carts running into each other. All right. So, we are going to get to practice conservation of energy. So, boom, this is good. The reason I put this problem is it's a good reminder that energy still exists. So, the energy I start with equals the energy. Look, I'll even write this. Energy plus work equals energy I end with. There's no work done. Like, in the collision, we're going to say no work's done. All right, great. Go through the checklist. What energies do I start with? Go through the checklist. What energies do I end with? Oh, also, you got to make a judgment call. Where do y'all want y equals 0? Anytime you all talk about energy, you need to define y equals 0. Where do y'all want y equals 0 in this picture? Make a judgment call. It doesn't matter. What's a nice place to pick as y equals 0? The ground. Great. Y equals 0 is the ground. Great. Fantastic. Are they moving to begin? Is object 1 moving to begin with? Is there anything moving in the beginning? Yeah, great. Which one's moving? Object 1, object 2, or both? So object 1 is moving. So it's got some velocity. Is object 2 moving to begin with? Nope, so it doesn't have energy. Great. Kinetic energy done. Am I above or below 0 to begin with? Remember we picked 0 where they started? They started on the ground, so nope, they're at 0. They are not above or below 0, they're at 0. So no gravitational potential. Any springs? No, great. Done. In the end, are things moving? Yeah, what's moving? Object 1 is moving. What about my boulder? Is my boulder moving? Yep, that one also has. If you have multiple objects, they just each get their own energy. Are they above or below 0? No. Are there any springs? No. Great. There's my conservation of energy equation. Now I have 2 equations with 2 unknowns. And again, I'm going to show you all the next step, but I'm not actually going to solve this problem. This is a system of equations. My 2 equations are this one that the energy one and the momentum one. And I'm going to go ahead and write that momentum one right down here. I'm going to rewrite it just to make it easier to see. M1 V1 initial equals M1 V1 final plus M2 V2 final. Two equations, two unknowns. The two unknowns being the things I'm going to highlight in yellow. V1F, V2F. V1F, V2F. Those are my unknowns. How do you solve a system of equations? You isolate one of the variables in terms of the other. So in this, we're going to solve for V1F by itself. We're going to get V1F by itself. How do we do that? We're going to subtract M2 V2F to the other side. I'm not doing anything crazy here. Literally all I did was I took this term and I subtracted it to the other side. Nothing wild. Great. Now what am I going to do? If I want V1F by itself, I'm going to divide everything by So M1 V1 initial minus M2 V2 final. I'm going to divide everything by M1. Why am I going to do that? Again, I'm just isolating the variable. I'm just getting it by itself. I'm just doing algebra. I'm getting V1 by itself. V1 was right here. I wanted it by itself. How did I get by itself? I subtracted this term to the other side. Awesome. How do I kick this M to the other side? I divided it over. Great. Why am I doing this? Here's where the unpleasantness happens. We then take this entire thing and we chuck it right here and square it and do numbers. That's the next step. It's algebra. It is algebra you all are capable of. So I'll write this last step kind of on here. Is it pleasant? No. So, great. I'm just going to show you all what this looks like, and then you could do it for yourself if you really want. So we get 1/2 M1 V1 initial squared. We know all those values. You just chuck those in there. Equals 1/2 times M1 times M1 V1 initial minus M2 V2 final, all divided by M1, square that whole thing. Plus the other thing, and then you solve, and then you actually, it's one, as crazy as it seems, this equation only has one unknown. The only unknown in this equation is V2F, so it's solvable. And you all do have the algebra skills to solve this, even if you don't believe it, you do. There's no crazy like calculus here. You would just square this, you FOIL it out. Then you would do, at some point, you do have to do the quadratic formula. Yeah. Anyway, I show this to you all just to show that this, what's the takeaways from this? Is the takeaways that you need to do this gross math? No. What is the takeaway? What do I need you all to know? I need you all to know this slide. The one I mentioned previously. This problem is just to emphasize the following slide. In an elastic collision, momentum is conserved and energy is conserved. That's really what I need you all to know. And to actually solve some of these problems, you sometimes have to use both. I am not going to give you a problem where you have to use both. But I could give you a problem saying two things collide. I mean, it's actually one of the concept checks for your all's next things. Two things collide in an elastic collision. What's conserved? Momentum, energy, both. Neither. It sounds a little silly, but it is important to identify what stays the same. Like, this is totally something they could ask on the MCAT. They like concept questions on the MCAT, and they could totally say two things collide, what is conserved, energy. Like, that is something I think they could ask. I'm not 100%. I still haven't bought an MCAT book, but I can see that being a thing. All right, so great. That's momentum. That's all the practice problems. Okay, next class, just to give you all a sense of it, we're not gonna do too much with it yet, but I just want to give you all a preview. This is what I'm going to teach you all next class. It's called center of mass. This equation looks more unpleasant than it actually is, okay? What we're going to learn is that you can find the center of an object. We're all like, you can basically take an entire object and pretend that it's located at a single dot. The center of its mass. It's in the name. It's the center of its mass. And how are you going to do it? It's x and y. You are going to sum up every object that's there, its x position times its mass, and then divide it by all the mass, and you're going to do the same thing for the y. What I'm going to hopefully convey to you all, the process for this, one of the problems I'm going to give you, is the same process that they use to calculate your GPA. So we're going to actually start doing our calculations for how to get your GPA based on credit hours and things like that. And if you're cool with this, center of mass is the exact same calculation. We just swap in different variables. So that's to give you some peace of mind. We'll do that next time and start fluids. It'll be great.